Today topic of discussion is semiconductor laser. As we will see in semiconductor laser basically how it will works, what is the role of semiconductor material, which semiconductor material we will use in this particular laser which is called semiconductor laser, what is the principle of laser, how population inversion is achieved into the semiconductor laser. These are basic questions which I have to cover in this particular lecture. Number one, which semiconductor materials or material is used in semiconductor laser, how it works, how population inversion is achieved in semiconductor laser, and what are the basic applications of the semiconductor laser. So these are few questions which I have to cover, but before I go into the detail of semiconductor laser, there are some basic fundamentals related to the laser. These are related to the absorption and emission. What is absorption and what is emission? These explain with the help of energy levels of an atom. Like this state E1 is correspond to the ground state of an atom. Suppose this is our atom is in ground state. E2 is the excited state of the atom. This is our excited state, ground state and excited state. What is means basically? What is ground state and what is excited state? Ground state means the atom basically which have normal electronic configurations, which are filled, these electrons are filled in those orbits according to the Pauli exclusion principle, and the distribution of the electrons in different energy levels are according to the half-bow rules. So if somehow we change the electronic configuration, that state is correspond to the excited state. For an example, I have this atom, this is nucleus, K cell, in which we know there are 2 electrons. L cell, there are 8 electrons, and like M cell, there are 18 electrons. Somehow this electron of this cell absorb the energy, that is h nu, and goes in a higher state. Suppose this one is N cell. So this electron absorbs the energy and goes into this particular cell in a particular orbit. So now the electronic configuration has been changed. So the first state before absorbing this photon is known as ground state, and now when this electron absorbs the energy and this electron goes into the different state, now the electronic configuration has been changed, and this kind of situation for this particular atom is known as excited state. So this is the basic idea of ground state and excited state. When this electron absorbs the energy, it will stay here up to 10 raised power minus 8 seconds. So this is our ground state. This atom absorbed a photon of h nu energy and goes into the excited state. This is called absorption simply, or sometimes it is called stimulated absorption. So now what will be the second situation? This atom absorbs the energy and goes into the excited state E2. Here, this is our excited state. Right now, atom is in excited state. Lifetime of the excited state is 10 raised power minus 8 seconds. This is our ground state. After 10 raised power minus 8 seconds, this atom jumps into the ground state and emits a photon of h nu. The direction of this photon will be random. This photon can go in this particular direction or in this particular direction. It is free to go here and there in any direction. So this is the case of spontaneous emission. Spontaneous emission. In spontaneous emission, the emitted photon can go in different directions. Now the third possibility is related to the stimulated emission. These two lines, these two energy levels correspond to the ground state and excited state. Still our atom is in excited state. A photon comes and induces this atom. As a result, this atom comes into the ground state after emission a photon of the same frequency as of the incident photon. This photon of h nu energy induces this excited atom, this excited atom, and as a result this excited atoms jumps into the ground state with a photon that have same frequency as of the incident photon. So we are getting two photons of same frequency and in same phase. So here frequency of the emitted photon and incident photon are same and both are in same phase. Both are in same phase. So now we have a one frequency, that means one wavelength, because nu is equal to c upon lambda. If nu is fixed, lambda will be fixed, c is a constant. So we have a constant frequency, a common frequency. That's why we say the emitted light is monochromatic. Light is monochromatic because of the single frequency, because of the single wavelength. And both photons are in same phase. That means source will be coherent. A laser source is coherent because all the photons which are emitted from the excited atoms are in same phase and of the same frequency. This case is known as stimulated emission. So in general, laser stand for light amplification by stimulated emission of radiation. So as the full form of laser is light amplification. We are amplifying the light by which process? Stimulated emission process of radiation. How we are amplifying the light? We are amplifying the light with the help of stimulated emission. There are three processes. One is known as absorption. Second, there are two possibilities of emission. One is spontaneous emission. Excited atom spontaneously jumps into the ground state, and secondly, this excited atom induced by a photon, and as a result we are getting two photons of the same frequency and both photons are in same phase. This process is known as stimulated emission. For the laser light, our requirement that stimulated emission dominates over the spontaneous emission. So for the laser light, we want stimulated emission only. So in semiconductor laser, how we achieve basically population inversion? That is the question, and that answer comes from this process which I have discussed here. So now this is the basic idea of absorption and emission. Now this semiconductor laser, so now the next question is, what type of semiconductor laser we are using? So what type of semiconductor material we are using? The same silicon or germanium, or that is different? Yes, that is different. For the semiconductor laser, we require such material which show optical properties. So gallium arsenide, we are using here gallium arsenide semiconductor material because this semiconductor material show the optical properties, while silicon and germanium show thermal properties when electron and hole recombination take place. So the basic structure of semiconductor material, silicon and germanium, where Z of silicon, atomic number of the silicon is 14, atomic number of the germanium is 32. The basic structure of the semiconductor material, that is known as intrinsic semiconductor material. Why we need it? Intrinsic semiconductor or extrinsic semiconductor. What is the requirement to explain here? Basically, there are many misconceptions related to the basic structure of the semiconductor. That's why I thought to explain about it. The intrinsic semiconductor, whether that is silicon or germanium. So I am taking here silicon. The basic structure of the silicon have outermost orbit 4 electrons. These 4 electrons make a covalent bond with the neighbor silicon atoms. So like this silicon, next silicon atom, here silicon, and these 4 electrons which are valence electron and making covalent bond with the neighbor. And so like this one, they can get stable configuration. So this is the crystal of silicon semiconductor material, where in outermost orbit cell they have 4 electrons. One is the electronic configuration of the silicon is 1s2, 2s2, 2p6 and 3s2, 3p2. So these are 4 electrons in third cell. So outermost cell we have only 4 electrons, and these 4 electrons are valence electron which make an covalent bond with the neighbor atoms like this. So these are covalent bond basically. I am making it with red color pen to make it more clear, if it is visible. So clearly these are the covalent bond, and this structure is known as intrinsic structure of semiconductor material. Whether that is, if I have choose here silicon, so it is intrinsic structure of the silicon, but if I choose germanium, then it will be germanium structure, intrinsic structure, pure semiconductor material. So this is pure semiconductor, intrinsic semiconductor material. Now if suppose I have to increase the conductivity of semiconductor material, so what I will do, I will drop some impurity into this. Impurity may be trivalent like aluminium, it may be pentavalent like phosphorus. So aluminium is trivalent impurity and phosphorus is pentavalent impurity. When I add here phosphorus, that is pentavalent impurity, and its atomic number is 15, so electronic configuration will be 2, 8, 5 according to this. So in third cell, K, L, M cell, that's have 5 electrons. 4 electrons of this phosphorus makes a covalent bond with the neighbor silicon atom, and it's have one more electron, one extra electron, that is loosely bound. With a small thermal energy at a room temperature, this loosely bound electron can easily move here and there in conduction band. So the representation of this crystal is, here I have considered pentavalent impurity. It's have one extra electron. If it donate one electron, it's have, the impurity will have positive charge or negative charge. The impurity will have positive charge because it's donor impurity. So phosphorus is a donor impurity, it will have positive charge. So that indicate by this positive ion, and it's have one extra electron, that representation is this one. So all this complete structure can be represented with a single ion and this electron. This is free electron. So corresponding to one impurity in this pure semiconductor material, we can represent it with the help of this symbol. So positive, here positive ion basically is related to this impurity ion, and that's have one extra electron. So this will be n-type semiconductors. The representation of n-type semiconductor will be, this is positive ion of the donor impurity, positive ion of donor impurity, that's have one extra electron, plus minus, so plus dot, dot represent to the electrons, so plus, this plus and dot, this plus and dot. This is n-type semiconductor. This is n-type semiconductor material representation. When I am using pentavalent impurity, then the extrinsic semiconductor or n-type semiconductor, because I have considered here pentavalent impurity, that's why I am getting this n-type electron as a majority charge carriers, right? That's why the representation of the combined this single ion and electron represent this picture. So if I am using the second one, it repeat the same one, and lower one repeat the same one, this side like this. So this is a combined picture of n-type semiconductor material. If I use here trivalent impurity, for an example, aluminum, that's atomic number 13. Aluminum, Z of the aluminum is 13. So its first cell have 2 electrons, second 8, and last one third will be 3 electrons. So these 3 electrons makes an covalent bond with the neighbor, and rest of the covalent bond we assume that a vacancy basically makes a covalent bond with this electron. This vacancy is known as hole. So the representation of this particular structure, here I have considered aluminum as a semiconductor material, as a impurity basically for the p-type semiconductor material. Aluminum is a donor impurity or acceptor impurity. Aluminum is a acceptor impurity. So the charge on this impurity ions will have negative. So this negative represent to this particular impurity ions, and it's have a hole. So this combined picture basically is symbolized with this negative ion and hole. Hole basically are the charge carrier for p-type semiconductor. So if I make a p-type semiconductor, so that will be negative and hole. This negative and hole. Negative and hole. Negative ion of the impurity, and that's a vacancy, right? So the majority charge carrier, these sides are holes. So these holes are associated with the acceptor impurity. This is n-type semiconductor material. This one is p-type semiconductor material. When we join these together, n-type semiconductor materials and p-type semiconductor materials, what happens? These free electrons starts to move towards the p-type, and hole start to move towards the n-type, and as a result electron hole recombination takes place. So this is the electron, these two represent to the electrons, and this open circle represent to the hole. That's a positive charge. So E plus. Here these are electrons, so we know these charge है E minus, representation by E minus. So E minus and E plus represent to the majority charge carrier. Here E minus electrons are majority charge carriers. So this is n-type semiconductor. Here majority charge carriers are holes. So this is a p-type semiconductor. When we are joining these together, so these three charge carriers, these are electron starts to move towards the p-type side, and these holes move towards the n side. So when electron hole recombination take place, this electron hole recombination taking place when we are joining these two semiconductor materials. So as a result, this region becomes like this way. So in this region there is no more free charge carriers. So now suppose this electron starts to move across this junction, but this electron see this negative ion, and here when this hole try to move this side, this hole see this positive ion, and as a result what happens, this stuff blocks and no further charge carrier flow through this junction. So as a result we see a depletion region across this junction. This region is known as depletion region. There are no free charge, and this behave like an electrode. This is positive electrode of a battery, and this is negative electrode of a battery. Have positive terminal, and this is a negative terminal. So in the absence of external biasing, there is no more flow of the charge carrier across this junction. So electron cannot move across the junction further, and similarly these holes cannot move further across this junction. So a barrier, internal barrier set up inside the PN junction without any biasing. But suppose if we apply external biasing to this PN junction, P positive terminal to the of the battery to P type semiconductor, and negative terminal of the battery to the N type semiconductor. So now this phase of the semiconductor material, what happens, this negative charge distribute and it force these free charge carriers, and similarly here at this phase the positive charge of the positive potential of the battery force these holes, and these holes starts to move towards the N side, and similarly these electrons starts to move towards the P side, and as a result we observe a current in forward biasing.